The wonderful world of binomials. The binomial expansions. So binomial, bi obviously meaning two, nomial meaning things, something that contains two terms basically. I guess that would be the most simplest of them all. 1 plus x to the power of 0, which of course is 1 because anything to the power of 0 is 1. Then we raise the power by 1, we get 1 plus 1x. Now I'm deliberately writing the coefficient of x in this case even though it's 1, just so we can draw out a pattern. 1 plus x squared, of course we know, is 1 plus 2x plus 1x squared. Our perfect cubed we know, but this is of course how we would get it. I'd just multiply the previous one by 1 plus x. I could do the same thing to create 1 plus x to the power of 4. A pattern starts emerging. Now that pattern is attributed to Blaise Pascal. Now, Blaise Pascal was not the first person to come up with this pattern. It's been known about for centuries. I mean, there's evidence of the Aztecs, the ancient Chinese cultures. I mean, Pascal's triangle, what we call Pascal's triangle, has been known for a long time. Starts with 1, but if we draw it like a triangle, there's the next one, 1, 1. So just looking at the coefficients, then it was 1, 2, 1. By drawing it like a triangle, the pattern becomes a little bit more obvious. So 1, 3, 3, 1, and we simply add the two numbers above, we'll get the number below. So there's our quartic, and we could keep going. So there's the pentic expansion, and keep going, power of 6, power of 7. There's beautiful symmetry about it, of course. There you go, power of 8, power of 9. Which then brings us to, wait for it, this is my personal favourite. I'm sure you have your own favourite, but this one's just got to be the best of them all, power of 10. I mean, how good is that one? I mean, look at it, look at it. Look. Because there's symmetry, but the middle number is 252, which in itself is symmetric. But then look at the numbers either side. 122, same digits, but moved around. I mean, how good is that row? That's my favourite one. We could keep going. There's power of 11. How far did I go? I've got room for 12. Did I do 12? Yes, I did. I think that's probably where I stopped. I don't know if I got room for 13. But you could keep going and keep going. So if we have to expand out 1 plus 2x on 3 to the power of 7, I can now do it, well, for want of a better word, quite easily. Still a bit of work to do. Because all we do is we start with the first term, which is 1, raised to the power of 7. The power of 1 goes down by 1. Then the power of 2x plus 3 goes up by 1. So the two powers will always add to be 7. And I just have to also remember to multiply each term by those binomial coefficients. So the pattern for 7 was 1, 7, 21, 35, 35, 21 and 7. Oh, and 1, I forgot the 1 at the end there. As I say, still a bit of work to do, but we could then come up with our expansion. Certainly quicker than actually going 1 plus 2x on 3 times 1 plus 2x on 3 times, and expanding all that out and collecting like terms. Now, here's where it, well, used to be very useful, I guess before we had our calculators and what have you, but if you had to find something like this, 0.998 to the power of 10, we only want it to 8 decimal places, we could use 1 minus x to the power of 10. So there's the expansion for 1 minus x to the power of 10. And all I do is substitute in 0.002 for x. But I don't have to substitute it into every term because I only want 8 decimal places. And once I get to a certain power, 0.002 to that power, or power of 4, will be 0 to 8 decimal places. I don't need the rest of the terms. So I only have to work out these 4, and then we could come up with the answer. Now if I have to find a particular coefficient in this expansion, well, I'll expand out the second one when I'm not going to bother working out what each term is because I'm not interested in every term. I'm only interested in the ones that will produce x squared. So the 2 would be multiplied by this term here, the 6 times 4 squared times 5x squared, and the minus 3x would be times the one before that, so 4 cubed, 5x. They're really the only ones I'm interested in. And notice it says find the coefficient. So I don't worry about the x squared. I'm just interested in what's in front of it. 2 times 6 times 4 squared times 5 squared minus 3 times 4 times 4 cubed times 5, which we can easily work out to be 960. That will do us to start off with our look in binomial expansion.